Hey everyone, welcome to Code Harmony. Today we are going to cover LeetCode problem number 2097, valid arrangement of pairs. This problem is based out of the concept of Euler path or Eulerian path, which is an important topic in graph theory. And this question has been asked in meta. So this question is important for you to understand the graph theory concepts. Let's have a look on the problem statement. Here we will be given 0 index 2D array of pairs. And this pair is having starting and ending. And we have to arrange these pairs in such a way that every ending of previous pair is equal to the starting of current pair. Let me show you by example. What we are given? We are given pairs, couple of pairs. And these pairs we have to arrange in such a way that the ending of every pair is equal to the starting of the next pair, like this. First pair is ending at 9, second ending starting at 9, ending at 4, starting at 4, ending at 5, starting at 5. So the arrangement that we have to do is starting of next pair is equal to the ending of previous pair. So this is asked in the problem statement. If you are new to graph theory, I would highly recommend you go and check out this detailed video of Eulerian path and circuit. What is Eulerian path and what is Eulerian circuit? By watching this video, you will get more understanding on Eulerian path and Eulerian circuit, and you will be able to cope up with the problem very easily. And if you know some basics of Eulerian path, you can go along with me. Now the problem statement is clear to you. Here we will deep down on the given example. In the given example, we are expected to have the arrangement like this. So if I draw this example, we are going to get this graph, this directed graph where we are starting from 11 and we are ending at 1. So here in the representation, what are my pairs? First pair is 11 9, second pair is 11 9 4, then 9 5, then 5 1. If we check any pair, let's say the I equal to 1. First pair, if we see, first pair is 9 and 4. What is the previous pair? Previous pair is 11, 9 and 9. Ending of the previous pair is equal to the starting of the next pair. Ending of the previous pair equal to the starting of the next pair. In this way, we are doing this kind of arrangement. And here, just try to think that these pairs are the edges of directed graph. As we can also see from this example, these are the directed edges. And this is making a directed graph. If you try to analyze what we have done in this example, we are visiting every edge only once. We are starting from 11 and visiting every single edge only once. So this we are doing. If you are aware of the graph theory, then you get to know that this concept is called Eulerian path. Eulerian path is something when we are visiting every edge of a graph by once. Then that is called Eulerian path. And here, if I ask you what is the type of the graph type is directed because we have edges directions. Now we are clear that we have to get the Eulerian path. So whatever the problem is given to us, in the given inputs, we are given some pairs and you consider those pairs as the edges of directed graph. And what you have to get me is that Eulerian path of these edges. You have to arrange those edges accordingly that you are able to get the Eulerian path, covering every single edge once. Now we are getting the idea that we can somehow break down this problem and get some idea from the Eulerian path concept. Now let me help you revise the Eulerian path concept for directed graph. If I take this example, what is Eulerian path? Covering every single edge by once. Okay, and how many edges we have? We have 3 edges in this case. So we have to do some kind of arrangement where we are able to cover every single edge. If I draw the edges, we have 1 2 as edge, 1 3 as a edge and 3 1 as a edge. But if I cover all of these edges, I will start from 1 and go to 3. First edge is covered, then second edge is 3 to 1, that is also covered, and then 1 to 2, this is also covered. In this way, my arrangement will look like this. And it is also the same, that ending of the previous edge is equal to the starting of the current edge. So my first edge was 1 3, second edge was 3 1, and third edge was 1 2. First ended at 3, second started at 3, second ended at 1, third started at 1. In this way we have covered every single edge of this graph. Now this path, this arrangement will be called Eulerian path. And this is the same thing we have to do in the problem statement. The edges are given in some random order and we have to arrange those edges in such a way that we are able to get the Eulerian path. Now let's understand the requirement to be able to get the Eulerian path in directed graph. because that is already given in the problem statement. In case of directed graph, if n-2 nodes are having in degree equal to out degree and one node with extra out degree and one node with extra in degree, in this case we are definitely be able to get the Eulerian path. Okay, and in the problem statement itself it is given to us that the valid arrangement of the pairs will definitely be there. If the valid arrangement of the pairs will definitely be there, it will definitely be following this condition, Eulerian path. So what is that case? For all those n-2 nodes, we will use those nodes as our middle node and the node with extra out degree. Let's say there is only one out degree, there is no in degree. That node we can use for our starting node. So this will be considered as a start of our Eulerian path, and the node with one extra in degree will be treated as the ending of the path. If you look at the same example for Eulerian path, here this one is having in degree equal to 1 and out degree equal to 2, and this 3 is having in degree equal to 1 and out degree equal to 1. 2 is having in degree equal to 1, out degree equal to 0. So n is 3. N is the number of nodes. So number of nodes are 3 and there is n-2 nodes, which is one node. One node is having in degree equal to out degree. This 3 is having in degree equal to out degree. So this 3 is going to be my middle node. And what about the starting and ending node? 1 and 2. 1 will be the starting, 1 will be the ending. So let's have a look on the node with value 1. For the node 1, in degree equal to 1 and out degree equal to 2. So there is one extra out degree. So this will be treated as a source. For the node value 2, in degree equal to 1 and out degree equal to 2. There is one extra in degree. So this node will be treated as ending node. So we did the same thing. We started from 1, went to 3, then 3 to 1, then 1 to 2. Ended at 2, started at 1. So this is the path. And this was the condition, n-2 with in degree equal to out degree, 1 with extra in degree and 1 with extra out degree. If that is the case, we are able to get the Eulerian path. Let's say you tell me that what if all the nodes are having same in degree and out degree. Here in this graph, we are having 4 edges and every node is having in degree equal to 1 and out degree equal to 1. All the nodes are having in degree equal to out degree. In that case, this path is a special path, and this special Eulerian path will be called Eulerian circuit, because we can take any node as our starting node. Let's say take 1 as a starting node. I go to 2, 2 to 3, 3 to 4, 4 to 1, and we are ending at 1. So we are starting node and equal to ending node. So this is going to make Eulerian circuit. You can consider Eulerian circuit as a subset of Eulerian path. In the problem, it is given that the valid arrangement definitely exists. It means that there is definitely a Eulerian path. And if there is Eulerian path, there might be possibility that the path is starting and ending at the same node. If that is the case, we are going to have the Eulerian circuit. Even if we get Eulerian circuit, Eulerian path, we have the answer, we have to do the arrangement. If it is a Eulerian path, I will be taking node with the extra out degree as my starting node. If it is a Eulerian circuit, take any node as a starting node. Okay. So now the problem statement is reduced to find Eulerian path. That's all. This much we have to do. We are given number of edges and just we have to find the Eulerian path. If still you are not clear about the Eulerian path, I would recommend you to watch this detailed video on the Eulerian path and circuit. Now we'll have a look on the approach. Here our approach would be just find the Eulerian path from the given directed graph. The first step would be we have to prepare the adjacency by given pairs. Given pairs are the edges of this graph. So from those edges we have to prepare the adjacency and we have to track the in degree and out degree of every single vertex. Let's say these are the edges given to us and we have to prepare the adjacency out of it. For adjacency I can take a map. The 1 is having a neighbor 2, 1 is also having a neighbor 3 and 3 is having a neighbor 1. Okay, the adjacency list is prepared. Now just track the in degree. Here as we are iterating over this pairs and preparing the adjacency, we can do the capturing of the in degree and out degree during that iteration. Let's say this map is for in degree capturing and out degree capturing. Initially we are having 1 and 2. So here 1 is having 1 out degree and 2 is having 1 in degree. So 2 is having 1 in degree and 1 is having 1 out degree. In the next node, in the next edge is from 1 to 3. Now vertex 1 is having 1 out degree and 3 is having 1 in degree. So 3 is having 1 in degree and 1 is having 1 out degree. So out degree of 1 will be incremented by 1, which is 2. Now 3, 1. So here 3 is having out degree. So 3 is having 1 as out degree and 1 is having as in degree. So in degree of 1 is 1. Okay. Now the nodes are kept. Now the in degree, out degree and adjacency is prepared. Here comes the step 2. Step 2 is that we are definitely sure that the Eulerian path definitely exists there. Now we have to see whether the path is there or Eulerian circuit is there. Eulerian circuit is something that we can choose any node as our start node. But if it is Eulerian path, we have to pick the node or vertex where the out degree is 1 more than the in degree. So if the out degree is 1 more than the in degree plus 1 is equal to out degree, then that node can be treated as our start node. So first of all, we will check the out degrees of the graph. We are going to check out degrees. So let's say I pick all the pairs, and if out degree is equal to in degree plus 1, here for 1 out degree is 2 and for 1 in degree is 1. In degree plus 1 equal to out degree. So this 1 will be treated as our start node. And what about the destination node? So if I start from here at 1, I can go to 2 or 3. Let's say I go to 3 and for 3 to 2, and then in the end I'm coming to 2. So 2 will definitely have in degree 1 more than out degree. For 2 the out degree is 0 and in degree is 1. So this is satisfying our condition that n-2 nodes are having in degree equal to out degree and 1 node with extra degree, 1 node with extra in degree. So n-2 node. So 1 is my source, 2 is my destination. So source and destination. Apart from these two, what is the remaining one? 3. So for 3, in degree is also 1 and out degree is also 1. So okay, this is following our condition. And here in the step 2, we only need to capture the start node. Start node we have captured. 1 will be treated as our start node. Here we come to the third step, which is start the DFS call. DFS call, we are always going to start from our starting vertex. Here in this example, in this given example, my start is going to be 1 because 1 is having extra out degree. So my start is 1, and what I will do is I will visit every single neighbor of that current element. But when I'm adding that element in the resultant, after processing all the elements, when I'm coming back from the DFS, during the backtracking, I'm adding that element. We'll get to know once we do the dry run. If I dry run on the same example, here we are definitely going to start from the solution 1. Okay. Now I need to process all the neighbors of 1. 1 has a neighbor which is 2. I'm going to 2. So solution of 2 I'm calling. Now the solution function call of 2. 2 does not have any neighbor. It means that this while loop will not work, and after that we have to add the current element. If let's say I added the current element, 2 I added, okay, I'm returning back to 1. And there is some other neighbors which are remaining processing. Now come to the second neighbor. Second neighbor is 3. The second neighbor call is made solution 3 because it is a while loop on all the neighbors. 2 is processed. Now 3 will be processing. So solution 3. But 3 is going to further make a call to its neighbors. 3 neighbors are 1. Solution of 1. Now solution of 1 does not have any active neighbors now. All the neighbors are visited. So it means we are returning from this call. When we are returning from this call, during the backtracking, I am adding the current element, current vertex. So this 1 will be added to my resultant. So this is my resultant array. 2 was added in the starting and then 1 was added. Now all the elements, all the neighbors of 3 are processed. I'm returning from this call. I'm adding 3 in the result. Okay. Now I have come to my starting call. Starting call, when I'm returning from the starting call, I will add 1 again as well. Now this is the element we have captured. If you try to look on the right to left direction, first of all, you visited an edge from 1 to 3. From 1 to 3 you visited the edge. From 3 to 1 you visited the edge. And then from 1 to 2 you visited the edge. If you visit the edges in that order, 1 to 3, 3 to 1, 1 to 2, 1 to 3, 3 to 1 and 1 to 2, you are able to get the Eulerian path. So this reverse order is the Eulerian path. We have captured the Eulerian path. So this is the algorithm. Just start the DFS from our starting position, visit all the neighbors, and in the backtracking, add the element. So when you are adding throughout the DFS call, then it is not going to work. You have to add the element when you are backtracking or returning back from the DFS call. Okay, so this much we have to do. Yeah, so we are given edges. From those edges, just prepare the adjacency, and then adjacency along with the in degree and out degree. In the step 2, just figure out your starting node. In the step 3, just start the DFS call. Here one more note I have to tell you, that when you are traversing over these pairs, over these edges, then you are not marking vertices as visited. You are marking edges as visited. Let's say first edge in this case is 1, 3. You have to mark that edge as visited. So let's say in the adjacency, when you are coming from 1 to 2, you are removing 2 from this adjacency. If you mark this 2 as a visited, global visited, then let's say when you are going from 1 to 3, 3 you have marked visited. Now when you are coming here, you will be seeing at visited. It means that you just have to remove that element from the particular adjacency order, or you have to remove the particular edge. That you have to remove edge from U to V. If you are removing edge, this adjacency map, you can take this value as a DQ. You are inserting in the end and removing from the starting. So if you take the map as DQ, you will be able to remove the edge. So what was the note here? You have to mark edge visited, not the vertex. The edge should be marked as visited. Now let's have a look on the time and space complexity of this approach. Time complexity is going to be the number of vertex plus number of edges, because for every vertex we are preparing that in the adjacency, and we are processing every edge, because in the adjacency we have number of edges stored already, and we are processing every edge once. So E will be added to this. So time complexity will be the order of vertex plus edges. And what about the space complexity? For every vertex we are storing number of edges, so it will be the same, vertex plus edges, as per our adjacency matrix. So this is the time and space complexity. Now we will code this approach. Let's have a look on the code. This code is something that we have to get the Euler path of the given pairs. Given pairs are the edges. So first of all, our first step is that using these pairs we have to prepare the adjacency. Adjacency list is we have prepared, and we are using DQ here because we have to remove edges out of the adjacency, not the vertex. If we have to mark the vertex, we could have like just taken another separate visited set, but here we have to remove the edges. When we have to remove the edge, we have to remove the vertex from the value of that adjacency list. Now the adjacency list is prepared. Along with the adjacency list, I will also capture the out degree and in degree. For every pair, we have U and V. Edge is coming from U to V. So out degree of U is incremented by 1, in degree of V is incremented by 1. Okay. And this is the result I will pass to my DFS function. Now we have to capture the start. What is the start? In the Euler path, the start node is always going to be the one which is having out degree 1 more than the in degree. So if the out degree is equal to in degree plus 1, then that node will be the start node. Otherwise, just take the default, any one of the start node. In that case, we will going to have Eulerian circuit. Into Eulerian circuit, we can consider any node as the start node. Now we'll just call our DFS function. This is the heart of the code, and this DFS function you have to see. For every U, I'm like considering every neighbor. For U is my node, and I'm going my DFS call to every neighbor in the adjacency list. So I'm polling the neighbor and then making the DFS call. Why I'm polling here? Because that neighbor we have to mark as visited. It means that I am marking that edge as visited. So I'm polling it from my neighbor list. I'm making the DFS call. Once all the neighbors are processed, then I'm adding my current node, current vertex. So for, let's say, in our example that we discussed earlier, one was having two neighbors, 3 and 2. So when I'm processing 1 to 2, that edge I am marking visited by removing that 2 from the adjacency. Once the DFS call is over, my resultant list is going to have elements like this: 1, 5, 4, 9 and 11. Okay, but we won't answer in this form. So you just have to convert it and process it. First of all, we are reversing it. If I have reversed it, it is something like 11, 9, 4, 5, 1. Using 11, 9, 4, 5, 1, you can prepare your pairs. Now these pairs are in the order of the Eulerian path edges. And this is going to be our answer that we can return. Here on my code, sample test cases are passed. If I submit it, it should successfully submitted. Okay, the code is working fine. I hope this challenge is clear to you. It is based out of Eulerian path from graph theory concept. In case you have any doubt, you can discuss in the Discord community or comment down below. And I also want to congratulate all of them who are able to complete this challenge. Thanks for watching, guys. Bye bye.